Hi, this is our presentation for scenario week 2. So the first thing we decided to work on was the bill of materials, and when designing it we had to take some things into consideration. The first thing was the cost of each individual part to ensure that we stayed within budget. The next thing was that the parts are made from the right materials and of the correct masses used in our calculations. And lastly, to make sure that the items were not out of stock and that they were readily available. Now, when we were making our bill of materials, we did encounter some difficulties. One thing was quite a bit of time was spent looking for a motor that was suitable for the one that we used in our calculations, but eventually we managed to find the perfect one. And another problem we had was an item we had found had run out of stock, so we had to find an alternative replacement. And another problem was that some specifications weren't available from the data given to us from the websites, but we mentioned this in our bill of materials.
So we had some major changes to our design since scenario 1 to make it more efficient and more practical. So first off, we added a rack and a pinion to measure distance mechanically. We added a spring for deceleration, a switch for the vehicle to be able to change direction, bolts and nuts so that everything was clamped into place. And we also added a gears, rack and pinion that now mesh together on fusion as a completely animated model. More detail about the rack and pinion. So we have a motor that rotates at 600 RPM, and we have a gear ratio of 1 to 10, so therefore our pinion rotates at 60 RPM or 1 revolution per second. And since it takes 3.7 seconds to hit the wall, the pinion therefore does 3.7 rotations. And since its circumference is 29.7, the distance traveled by the rack is 110 millimeters. And we have 2 stoppers acting on the rack, which are 3D printed with the base. And they are placed at the distance of 110 from each other to measure distance mechanically on the way back from the wall.
So in the second week of scenario, the two most important factors will be the time taken and the energy used. In terms of energy, in scenario 1, we only consider acceleration of the beginning, the compression of a string, and acceleration after hitting the wall. However, this week we'll also consider the losses that the energy required has to overcome to keep velocity constant. They will be drag and the rolling resistance. So from previous assumptions, we can say that most of the energy is required in keeping a constant velocity, and this energy can be achieved by the equation E equals Rx, where R is the force due to the motor and X is the distance traveled, that is, about 3 meters. In order to calculate R, we'll have to equate it to the drag force plus the resistive rolling force, because when the velocity is constant, the net force in the system will be equal to 0.
So, carrying on from before, the simulation was generated with the aid of the provided iMechie software. This enabled us to visualize and emulate our previous paper and spreadsheet calculations, which helped us enormously to fine-tune aspects of the vehicle, such as its speed and energy consumption. These parameters were carefully aligned as our planned prototype would manifest, and hand calculations were done to sanity check the data outputted by the simulation. After deciding upon variable parameters such as mass and spring stiffness, we were eventually led to a good combination. The results depicted a fairly decent optimization of velocity and energy consumption, which we are very proud about.
This slide shows our final design, which I will talk about in the next slide. The main weakness of our design is the motor, because the dimensions of our actual motor are very small compared to the models available for import on Fusion 360. The data below in the example show why this is a problem. However, the fact that we are able to reduce our total mass in our actual vehicle compared to the mass of the CAD vehicle actually plays into our favor, because we are able to keep the mass of the actual vehicle under 500 grams. And so the weakness of the model can actually be disregarded in this sense, because the actual motor is perfectly fine.